Welcome, focused learners, to today's Explainer. I am absolutely thrilled to dig into this one with you because we are looking at some seriously mind-bending source material today. We're weaving together advanced mathematics, artificial intelligence, and, most importantly, the actual everyday reality of building software products. We're going to break down a recent event that's not just some massive AI milestone, but a complete reframing of how we should all be thinking about AI autonomy in our own work. It's a real game changer.
Okay, let's dive into this. What on earth does an 80-year-old math conjecture actually have to do with the future of software development? I know, it sounds like a massive leap, right? On one hand, you've got pure, abstract, historical geometry, and on the other, the super messy reality of actually shipping code and managing products. But, as you'll see, answering this exact, seemingly paradoxical question is the key. It literally unlocks the secret to making AI work autonomously in the real world.
So, Section 1, the 80-year math mystery. From Paul Erdős to autonomous AI.
To really grasp the weight of this breakthrough, we gotta have to look at the sheer historical scale of this discrete geometry challenge. It's like a giant puzzle that's been sitting on humanity's desk for decades. Way back in 1946, the legendary mathematician Paul Erdős posed the unit distance problem. 30 years go by, and in 1976, we get the first computer proof of the four-color theorem. Huge landmark for sure, but it was heavily human-guided. Fast forward to 2010, Guth and Katz make waves by presenting an almost tight lower bound. But then, May 20, 2026, everything changed. An internal, general-purpose reasoning model from OpenAI autonomously disproved the Erdős conjecture. It wasn't handed a step-by-step strategy. It just figured it out, entirely on its own. What this model managed to find was a completely stunning counterexample. Up until that point, the assumed upper bound was tied to a specific constant. But the AI used complex algebraic number theory to construct a scenario yielding way more unit distances than this previously assumed boundary of n to the power of 1.014. It absolutely shattered an 80-year-old mathematical assumption. Just poof, gone. And listen, this wasn't just a neat little parlor trick. Look at the reaction from Tim Gowers, a literal Fields medalist. He directly called this a milestone in AI mathematics. When a Fields medalist uses that kind of emphatic language to describe an autonomous AI capability, that carries immense scientific gravitas. It proved once and for all that a general-purpose model could do genuinely new, research-grade mathematics, completely without human handholding.
Which brings us to Section 2, milestone or hype. Let's decode the internet's reaction.
As you can probably guess, when this news broke, the tech world completely exploded. But it forces us to ask, does this mean artificial general intelligence is suddenly ready to just step in and run our businesses autonomously? Now, to be fair to the hype, there was an astonishing domino effect right after that May 20th announcement. Anthropic's system autonomously repeated the unit distance disproof. Inspired by that, Thomas Bloom and his team disproved the Erdős-Summerdy sum product conjecture. The Elicus-Ronii problem, completely disproved. DeepMind jumped in and solved multiple open problems using lean verification. Honestly, the idea spread like wildfire. It genuinely looked like AI was conquering all of higher mathematics overnight.
Now, what's really interesting about this slide is the stark contrast between that internet hype and the actual messy reality of product building. The hype goes something like this. Wow, an AI did original math, so obviously it can seamlessly run my business now, right? But the reality is completely different. Math is a highly unique domain because it offers free, perfect verification. Your business? Well, your business is full of subjective judgment calls, unwritten rules, and messy contexts. Let's dig into why that is in Section 3, the verifiability principle. Why math is the easy case for AI.
This principle from the SoftTech Infra blog is the hidden mechanic explaining exactly why the AI succeeded so brilliantly in geometry and yet why it might still struggle with your company's software. So, the crucial point is this definition of a self-certifying problem. This is a situation where a counterexample or a solution can be verified perfectly and instantly by a cheap mechanical checker. In math, a counterexample checks itself. This free verification is what allows the AI to loop endlessly, generating, checking, retrying, entirely without human judgment slowing it down.
Let's connect this directly back to your daily work. Think about your product for a second. There is no magical, mechanical oracle. You can just ask, hey, is this customer support reply good? Or is this generated invoice totally compliant? Actually, you are the oracle. AI autonomy ends exactly where your ability to cheaply verify its output ends. If this system cannot mechanically check itself, it absolutely needs you.
And this brilliantly illustrates that exact dynamic. Look at how safe autonomy scales precisely alongside cheap verifiability. Right up at the top, for math or code with a strong test suite, verification is cheap, so autonomy is super high. But as you move down the list into things like customer-facing copy or financial compliance actions, verification starts relying on human taste, subjective judgment, and real-world viability. In those unverifiable areas, autonomy remains really low. You absolutely need a human in the loop for those.
So what do we do about it? Section 4, the builder's blueprint, manufacturing verifiability for your software. How do we actively use this lesson to manufacture verifiability and safely leverage AI today? Consider this specific anecdote. Indian product teams are already putting this into practice. Real-world applications like Softtech Infra's exam-ready platform are actively separating their verifiable workflows from their subjective ones. They purposefully use mechanical rubrics to cheaply verify multiple-choice questions, which gives the AI really high autonomy there. But for the subjective essay grading, where there's no cheap verifier available, they strictly rely on human review or human-graded golden sets.
Let's move to and see how this builds into a highly actionable 4-step checklist for building AI products right now. Step 1, write the checker first. If your code can check it via schemas or regex, the AI can lean on it. Step 2, convert that messy human judgment into measurable golden sets. Step 3, let the model loop autonomously. Let it generate, check, and retry against your verifier. And step 4, keep a human firmly on that unverifiable tail where liability and taste live. Which leaves us with this final, really provocative thought. Are you just waiting around for an autonomous AI to magically understand and run your product? Or are you actively building the cheap verifiers required to unleash it safely today? The Erdős breakthrough shows us that verification and autonomy, they're actually the exact same problem. Well, thank you so much for joining me for this explainer. I hope this empowers you to completely rethink your software architecture. Keep learning and keep building.